An Introduction to the Theory of Automorphic Functions by Lester Ford. Chapter 1, Linear Transformations. Section 4, Inversion in a Circle. There is an intimate relation, as we shall see presently, between the linear transformation of the complex variable and the geometrical transformation of the plane, known as inversion in a circle. Consider a circle with center at O and of radius r. Inversion in the given circle is the transformation resulting from replacing each point P of the plane by a point P' lying on the line OP and whose distance from O satisfies the equation OP' times OP is equal to r squared. P and P' are said to be inverse with respect to the circle. If O, P, and P' have the coordinates fg, xy, x', y', respectively, the equations of the transformation are x' minus f is equal to r squared times the quantity x minus f, all divided by the quantity x minus f squared plus the quantity y minus g squared. Y' minus g is equal to r squared times the quantity y minus g, all divided by the quantity x minus f squared plus the quantity y minus g squared. If the center O moves to infinity, the circle becomes a straight line. The point P' approaches a position such that the line PP' is perpendicular to and is bisected by the given line. That is, inversion in a straight line is a mere reflection in the line. We state here for reference some well-known properties of inversions. Alpha. Angles are preserved in magnitude but changed in sign. That is, the transformation is inversely conformal. Beta. Circles are transformed into circles, the straight line being included as a special case of the circle. Gamma. 2 points inverse with respect to a circle C are transformed into 2 points inverse with respect to the transformed circle C'. The connection between inversion and linear transformations arises from alpha above. The inversion is a one-to-one transformation of the plane into itself, which preserves the magnitude of the angle but changes the sign. If now 2 inversions, or any even number, be made in succession, the result is a one-to-one transformation of the plane which preserves both the magnitudes and the signs of the original angles. According to Theorem 7, such a transformation is a linear transformation. Hence, Theorem 8, the successive performance of an even number of inversions is equivalent to a linear transformation of the plane into itself. The converse of this theorem will now be proved. The transformation z' equal to az plus b divided by cz plus d can be broken up into the succession of the following transformations. A. z1 equal z plus alpha, where alpha is equal to d divided by c. B. z2 is equal to e to the I theta times z1, where c squared divided by the quantity ad minus bc is equal to a times e to the I theta, and a is greater than 0. C. z3 is equal to a times z2. D. z4 is equal to minus 1 divided by z3. E. z' is equal to z4 plus beta, where beta is equal to a divided by c. That these are equivalent to the given transformation is verified by eliminating z1, z2, z3, and z4. We shall show that each of the 5 transformations is equivalent to an even number of inversions, which proves that the given general linear transformation is equivalent to an even number of inversions. A. Putting z equal to x plus iy, z1 equal to x1 plus iy1, alpha equal alpha prime plus I alpha double prime. The transformation on breaking into real and imaginary parts is x1 equal to x plus alpha prime, y1 equal to y plus alpha double prime. This is a translation. Let O alpha, figure 1, be the line joining the origin to the point alpha. Each point of the plane is translated parallel to the line O alpha, a distance equal to the length O alpha. Let ABCD be two lines perpendicular to O alpha and at a distance 1/2 O alpha apart. A reflection in AB, as in figure, followed by a reflection in CD, is equivalent to the translation under consideration. Thus, A is equivalent to two inversions. Footnote: we note that in this and succeeding cases, it is sufficient to verify that 3 points are transformed alike by the even number of inversions and by the linear transformation. This follows from Theorem 5. In the present case, we note that the points on AB are unchanged by a reflection in AB and are carried parallel to O alpha, a distance equal to the length O alpha by a reflection in CD. B, expressing e to the I theta in the form cosine theta plus I sine of theta, we get in this case, equating real and imaginary parts of the two members of the equation, x2 equal x1 times the cosine of theta minus y1 times the sine of theta, y2 equal x1 times the sine of theta plus y1 cosine of theta, a rotation about the origin through an angle theta. Let A' A and B' B be two lines through the origin such that the angle AOB is 1/2 theta, figure 2. We verify at once that a reflection in A' followed by a reflection in B' B is equivalent to the rotation in question. This case is thus reducible to a pair of inversions. C. This is the case of expansion from the origin. x3 is equal to A times x2, y3 is equal to A times y2. It is equivalent to the two inversions. 1. An inversion in a circle center at the origin and of radius r, followed by 2. An inversion in a circle center at the origin and a radius r times the square root of a. For if P', P" are the successive positions of P, OP" is equal to A r squared divided by OP' is equal to A r squared divided by the quantity r squared divided by OP is equal to A times OP. D. x4 plus iy4 equal to minus 1 divided by the quantity x3 plus iy3 equal to minus x3 plus iy3 divided by the quantity x3 squared plus y3 squared. Or x4 is equal to minus x3 divided by the quantity x3 squared plus y3 squared, and y4 is equal to y3 divided by x3 squared plus y3 squared. This is equivalent to an inversion in the circle with the center at the origin. x0 equal to x3 divided by x3 squared plus y3 squared, y0 equal to y3 divided by x3 squared plus y3 squared, followed by a reflection in the imaginary axis, x4 equal to minus x0, y4 equal to y0. E. This, like A, is a translation. Combining these results, we get the converse of the preceding theorem. Theorem 9. Any linear transformation is equivalent to the successive performance of an even number of inversions. It is evident that the representation of a linear transformation as a succession of inversions is not unique, that the transformation can, in fact, be broken up into an even number of inversions in infinitely many ways. The properties of inversions furnish us with valuable information concerning linear transformations. Thus, beta and gamma preceding yield the following important theorem. Theorem 10. When the complex plane is subjected to a linear transformation, A. Circles are transformed into circles. B. If 2 points are inverse with respect to a circle, the transformed points are inverse with respect to the transformed circle. Since 3 points determine a given circle can be transformed into a given circle by setting up a transformation carrying 3 distinct points of the first circle into 3 distinct points of the second circle. Theorem 5. These points can be chosen in infinitely many ways. Hence, Theorem 11. There exist infinitely many linear transformations which transform a given circle into a second given circle. Corollary. There exist infinitely many linear transformations which transform a given circle into itself. An Introduction to the Theory of Automorphic Functions. This book was written by Lester R. Ford, M.A., Harvard, lecturer in mathematics in the University of Edinburgh. It was published in 1915 by G. Bell & Sons Limited, London, and is now in the public domain. It is read by Jim Renhold with programming and illustrations by Jim Renhold in 2019. Thank you for listening.